So we'll be making use of the Maxwell's equations that we have derived in the last lecture. So in this lecture, we are going to look at the phasor form, which you might have already studied in your networks and everything. And then we are going to look at the point form of Maxwell's equation. And if we have time, we will also derive the wave equation. Okay. So the Maxwell's equations are very important because we'll be using it till the end of this course. We'll be reusing the equations and again to even for the wave equation, we are going to derive the wave equation using the Maxwell's equation. Okay. So let's look at the first point, which is the phasor form. This you might have already studied in your networks, but let me explain it again. So let's say there is a complex number Z, and I can represent the complex number Z as x plus jy. Okay, where x is the real part and j is the y is the imaginary part, which has the coefficient j. So j is defined as root over minus 1. Now, along with this complex number representation, I can also represent, so this is called as the rectangular form of representation. Similarly, I can represent Z as R e raised to j phi, where R is equal to root over x square plus y square, and phi is equal to tan inverse the complex coefficient, which is y by x. And this is called as the polar form. Okay. Now, we know the expansion of e raised to j phi, which is cos of phi plus j sine of phi. And similarly, if you do e raised to j of omega t plus phi, because let's give a time variable also. So this is basically cos of omega t plus phi plus j sine of omega t plus phi. Now all the voltages and currents that we regularly see in our circuits, which is basically the AC values, has of the form, for example, I can represent as some I0 cos of omega t plus phi. Similarly, the voltage also. So this I can write as the real part of I0 e raised to j omega t plus phi. Because when you when you take the real part of e raised to j omega t plus phi, which is cos omega t plus phi, and I0 is some constant. Or you can expand this as real part of I0 e raised to j omega t into e raised to j phi, which I can combine the I0 and e raised to j phi as real part of some I0 dash e raised to j omega t, where I0 dash is I0 e raised to j phi. Okay. Now, why we want to represent it like this? See, the whatever be the current or voltage, there will always be this time dependent term, which is cos of omega t plus phi or sine of omega t plus phi. So that means we'll always have e raised to j omega t term. So whenever you try to use the value of I, you don't want to explicitly specify that there is this time dependent term because it is already there. Instead, I will just specify that, okay, the value of my current is in phasor form is something like IS is equal to I0 dash, where IS is the phasor form. That means we don't explicitly specify the time dependence. As it is always there. Because time dependence is always there. So you don't want to specify every time that, okay, there is e raised to j omega t, I is equal to I0 e raised to j omega t. When you do some operations, again, you don't specify e raised to j omega t. You don't need that. You just say that, okay, I have a phasor form in which I know the time independent part. Okay. So this is to just to give an example. This we are going to our electromagnetic soon. Okay. Now coming to our electromagnetics, we have electric field and magnetic field. Electric field and magnetic field will depend on the space coordinates x, y, z, and also will depend on time. So this x, y, z is called as the space coordinates, and t is basically time. So if you consider a Cartesian system, okay, so electric field at any point will depend, let's say I am calculating electric field at this point, will depend on the coordinate of this point, let's say which is x, y, and z, and also at what time we are measuring the electric field. Okay, so basically time will also come into picture. Similarly for magnetic field. And the space coordinates and time are independent. Okay, that means I can represent E as some function of x, y, z. For example, I'll just give as E a of x comma y comma z and a function of t. And the function of t is mostly by the sinusoidal function, which is cos of omega t plus phi. For example, I can write E as, this is an example, x square plus yz into cos of omega t plus phi. Implies my electric field at points 1 comma 1 comma 1 is equal to 1 plus 1 into 1 into cos of omega t plus phi, that is 2 cos of omega t plus phi. Okay, this is just to give an example. So you see that you can separate the time dependence and the space dependence. So this is the space dependence and this is the time dependence. And if you compare this with our current equation, which we have looked upon in terms of phasor, it is almost similar, except that the I0 dash is basically, or I0 is basically x square plus yz. So I can write E as the real part of EA into e raised to j omega t. Or let me say this as ES, e raised to j omega t, where ES depends on the coordinates x, y, and z. Or to be more precise, this is e raised to j omega t plus 5. Okay, and this ES is the phasor form of E. So the phasor form of E is given as ES. So you see, in phasor form, there is no time dependence. That is, it is not a function of time. Fine. Now let's do one thing. Let's differentiate E with respect to time. Okay, so this is equal to dou E by dou T. So this is equal to dou by dou T of real part of ES e raised to j of omega t plus 1. So let's take dou by dou t inside of real. So this is real of dou by dou t es e raised to j omega t plus 5. Now we already told that es is independent of time. So es is also a vector. So es is independent of time. Okay. So when you do the differentiation, es is a constant. So it is equal to es dou by dou t e raised to j of omega t plus 5. Which when you differentiate, you will get the real part of j omega es e raised to j omega t plus 5. So that is equal to j omega into e, because this is, you can take j omega out. So this is real part of es e raised to j omega t plus 5. Okay. So this is actually your E. So you can, when you differentiate any vector, the phasor for the new vector will be j omega into E. Okay. Or I can say this as j omega into ES also. Right. Similarly, when you integrate dou E by, sorry, when you integrate E with respect to T, you will get, or you can transform it as ES by j omega. Okay, so here you can do one more thing, is you can say that the new value of ES. So I can consider this value as my new ES. So I can say that the new ES, when you differentiate, is j omega into ES. Similarly, when you integrate, is ES by j omega. Okay, so this here, make sure that the differentiation or integration is with respect to t. If it is with respect to x, y, or z, then that is a totally different scenario. Okay. So with this knowledge, let's look at the Maxwell's equations. Okay. So one of the Maxwell's equation is del cross E is equal to minus dou V by dou T. So this was one of our Maxwell's equations. And this we have derived from Faraday's law. So I can write this as del cross the real part of Es e raised to j omega t is equal to minus dou by dou t. B is also a vector, implies I can write it as the real part of Bs e raised to j omega t. Basically, we have represented by separating the time dependence and the space dependence. Okay. Now this term I can take del inside. Okay. So you'll have, so the del cross real part is equal to real part of the del cross of vector. So I can write this as a real part of del cross Es into e raised to j omega t. Why? Because del is, if you remember, it is dou by dou x, dou by dou y, dou by dou z, which will affect only the Es because Es is the space dependent part. And e raised to j omega t is time dependent, because of which the del cross will not have effect. So del is basically dou by dou x, dou by dou y, and dou by dou z. And Es is a function of x, y, and z, because of which you can do this. Similarly, I can write this is equal to minus the real part of Bs into dou by dou t of e raised to j omega t. Why? Because Bs is a function of x, y, and z, and we are differentiating with respect to t, which will only influence e raised to j omega t. Okay, and we know the right hand side is minus j omega into, or let me do it in completely in phasor. So the left hand side, you can write this, the new del cross. So this is your new Es. Okay, so the phasor terms of left hand side and right hand side should match. Okay, so in the right hand side, it is minus real of j omega bs e raised to j omega t. In the left hand side, it is real part of del cross es e raised to j omega t, implies I should match this. If both should be equal, then del cross es should be equal to j omega bs. So I can write del cross es is equal to minus j omega bs. Okay, and remember, es and bs are the phasor forms. Okay, so this is called as the point representation of Maxwell's equation, where you represent the Maxwell's equation in terms of the phasor forms, and es and bs depends only on x, y, z, or r theta z, or r phi theta, whichever coordinate system you are using. It will not depend on, so this will not depend on time t. Okay, so that is your point form. So let's write all the Maxwell's equation in point form. So original Maxwell's equation, and the point form. The first one is del cross D is equal to rho V. There is no differentiation or there is no integration. So I can directly write this as del dot ds is equal to rho ds. If rho is dependent on time and space. So I just wrote as rho ds. Next is del dot b is equal to 0. Again, there is no integration or differentiation, so I can directly write as del dot bs is equal to 0. The next is, we have already derived this, del cross E is equal to minus dou b by dou t. Since there is a differentiation, we already derived that del cross Es is equal to minus j omega ds. The last one, del cross H is equal to j plus dou d by dou t. So I can write in point form as del cross Hs is equal to, so j doesn't have any kind of differentiation or integration, so j will remain as js, the phasor form of j, plus there's a differentiation with respect to d, so we'll have j d omega ds. Sorry, j omega ds. So now you have represented the Maxwell's equation in the point form. So why we did this? Because you see that all the differentiations has just moved to some multiplication of j omega. So when we analyze more into this equation, we don't want to do any complex differentiation. We just need to multiply it with j omega. So this will help us in the analysis and the future derivations very easy. Okay, so this is regarding the point form of Maxwell's equation. Okay, so I hope you have understood this. This is a very simple part where we derive the phasor form and then we derive the point form. So now we'll try to do some analysis or some derivations directly using Maxwell's equation, and then we will try to do it also using point form. So whichever is easy for you, you can take both. Okay, but I don't know which one it will be asked in your question paper. Okay, fine. Okay, now let's start with electromagnetic waves. Okay, it's also called as EM waves. So what is a wave? Wave transports energy. So there is a limited amount of energy associated with every wave. So it will transport an energy from one point to other. For example, voltage. Voltage can be considered as a sine wave. It will transport from one point of the circuit to other. Similarly, electromagnetic wave transports energy in free space. Okay. Second, it is a function of both time and space. Means if you fix time, if you have some method in which you can say that I am stopping the time, then the wave will change as you move in the space. Similarly, if you are standing at a fixed position and if you look at the wave at different times, the wave will change according to time also. So the wave changes according to space and time. Okay. And the waves, this EM waves, are described using wave equation. Okay. So when you say it is a wave, then there's an equation associated with the wave, and we are going to derive that equation. There is a general wave equation. We are going to show that Maxwell's equation will give you the form of a general wave equation. Okay, and the electromagnetic wave will have both electric and magnetic fields, and both will be perpendicular to each other, and both will be perpendicular to the direction of propagation. Okay, so all these things we are going to derive. So let's look at derivation of wave equation from Maxwell's equation. We're going to derive the wave equation. Okay. Now we are going to do an assumption, first of all, saying that the medium or the medium in which the wave is going to propagate is source free. Means the value of rho v is equal to 0. I can write del dot d is equal to 0. That is equal to del dot. This is an assumption that we are going to make, because when the wave travels, the wave might not, or the medium will not have a free electron or a free charge, or there won't be a source on that medium. Okay, so this is a trivial assumption. It will not cause any damage to our complete analysis. Okay, so let's start. So as per Maxwell's equation, del cross E is equal to minus dou B by dou T. And you know that the value of magnetic flux density is mu into H. Implies del cross E is equal to mu into dou H by dou T. Okay. Now let's take curd on both sides. So I can write del cross E is equal to del cross minus mu dou H by dou T. Right? So del cross E is equal to minus del cross minus dou mu into dou H by dou T. So I can take the cross product inside. So I can write as mu dou by dou T del cross H. Okay. And we know that del cross H is equal to J plus dou D by dou T. This is again from Maxwell's equation. Where J, I can write it as sigma into E. This is from Ohm's law. J is conduction current density, which you can write as sigma into E, where sigma is called as the conductivity and E is the electric field. And D is equal to epsilon into E. So I can substitute this. So del cross H is equal to sigma E plus dou by dou T epsilon. Okay. So let me number this equation. So let's say this is equation number 1. Okay. So this is equation number 2. So I substitute equation number 1 in 2, because of which I will get del cross E is equal to minus mu dou by dou T of sigma E plus dou by dou T of epsilon E. Okay, let's say this is equation number 3. Now, the left hand side of 3 is del cross E is the vector triple product. This we have already seen the expansion as del of del dot E minus del square E. But we have assumed that the medium is source free, which means rho V is equal to 0 or del dot E is equal to 0. Okay. So this means this is source free, implies del dot E is equal to 0. So I can write this as minus del square E. So I can write, so let's say this is equation number 4. So using 3 and 4, we have minus del square E is equal to minus mu dou by dou T of sigma E plus dou by dou T of epsilon. Okay. And you cancel the minus sign at both ends. So we'll have del square E is equal to mu dou by dou T sigma E plus dou square by dou T square epsilon. So I can in general write del square E is equal to mu sigma dou E by dou T plus epsilon dou square E by dou T square. And this is actually a general form of wave equation in terms of the electric field. So this is the wave equation in terms of the electric field. Okay. Now, if you do in a similar manner, so we have started here with del cross E. If you have started with del cross H or del dot H or del dot E, then you can do a similar way to derive the equation in terms of magnetic field. So I can write del square H. So in similar steps, or using similar steps, we can derive del cross H is equal to mu sigma dou H by dou T plus mu epsilon. Sorry, there is a mu which I missed in the first equation. There is a mu here because you take mu inside the bracket. Mu epsilon dou square H by dou T square. And this is the wave equation in terms of the magnetic field. Okay. So I give you this as a homework where you derive the wave equation in terms of magnetic field. And you can also derive the wave equation in terms of the point form. Okay. So let me number this. Let's say this is A, this is B. Now from A, you can say del square ES, okay, is equal to mu sigma dou E by dou T will give you J omega ES plus mu epsilon dou square E by dou T square will multiply J omega twice because you are differentiating twice into ES. Okay. So this is equal to mu sigma J omega ES plus or minus mu square epsilon omega ES. Okay, or I can write in general, you can just take J omega mu out and I can write as sigma plus J omega mu into sigma plus J omega epsilon ES. Okay, this is del square ES. So this is the wave equation in point form or in the phasor form. So this is wave equation in point form. Okay. So what did I do? J dou E by dou T is J omega ES, which we already did, and dou square E by dou T square is equal to dou by dou T of dou E by dou T, which is equal to you multiply J omega twice and multiply with the phasor form. Okay. Similarly, I can write del square HS is equal to J omega mu into sigma plus J omega epsilon HS. So these are the wave equations in point form with respect to the electric field and the magnetic field in the phasor forms actually. Okay. So that completes our derivation of wave equation, electromagnetic wave equation in point form and in the differential form. Okay. So make sure you do this homework because this will help you in understanding that derivation much better. Okay. And also you can do the point form derivation from the start. Like instead of converting the final equation into point form, you can start with the point form. That means here itself, you can start with the point form saying that this is del cross E is equal to minus j omega mu into h. You can start it from here, okay? And then you can continue, and you will also reach the same equation. Okay, so that completes our derivation of wave equation. The next class we will look at how to solve the wave equation and find out and analyze the result. So this we have actually already seen in transmission lines. The equation is similar to that the voltage equation in transmission lines actually. And we see that there will be a transmitted wave and reflected wave. And similarly, in here also, we will see that there will be a transmitted wave and reflected wave. And there's a propagation constant, there's an attenuation constant. So whatever we have did in the transmission lines will come into picture here also. Okay, but here it will be with some extra terms, etc. But the concepts that we used in transmission line is applicable here also. Okay, so we will stop it here, and make sure you look at our last lecture also, which I have recorded. So that is a very important lecture. We couldn't do that in live class because of my laptop problems. Okay, fine. Okay, if anybody have any doubts,